and the lecture material based on the book Object-Oriented Software Engineering, Practical Software Development Using UML and Java. One of the things I first want to do is give you a little bit of a tour of the website for the textbook, because there's a lot of useful information that you'll find on the website that is not directly in the textbook. Okay? Among the things that you'll find are a set of links to software engineering websites. Okay? These links are found, there's information about them are found at the back of each chapter in the book, but they're online handily for you, so you don't have to type the URLs in. You'll also find that some of the websites change a little bit, so as I find that the links go dead because they change the URL, I adjust this website. So there's a lot of useful stuff about all aspects of software engineering available for you to look at that backs up what you find in each chapter. Okay. The second thing which you'll find useful as resource material in this book is a knowledge base which contains all the concepts found in the book. Okay? So on the left-hand side here, if I scroll this down, you'll see a long list of software engineering-oriented terms and words. Okay? You click on any one of those, you'll find detailed information about that concept. Now, this is based on the material in the book. I had a knowledge engineer go and extract all the information out of the book and basically put it on the web as little factoids, or little facts, pieces of knowledge in this knowledge base. And it's all hyperlinked. For example, let's imagine that I see API as an acronym, and I don't know what it means. I can click on that, and over here it says it's an abbreviation for Application Program Interface. Oh well, I don't know what that is either. So I can click on that, and it'll jump to the term in the list defining Application Program Interface, and it'll say this has a definition, which is a set of procedures or methods through which a layer provides its services. Okay, and then I say, well, okay, fine, but I don't know what a layer is. Well, I can keep on going. Okay, it has definitions of all these things, and the definitions, by the way, are the same definitions you'll find in the glossary in the back of the book. But the website has more than definitions. It has other kinds of things like examples and many other bits of information about each of these concepts. It says, for example, that a layer is a kind of component, okay, and gives you information about that. It also talks about the kinds of layers, okay. So, for example, one kind of layer is a kernel layer, and then you click to that and you see what a kernel layer is. Okay, so this is a useful resource for you to help you study. If you don't understand a term, you can go look it up on the web, and hopefully that will help you to learn the material in this course better. One of the things about this course and this book is it's designed to give you a very broad introduction to the core concepts of software engineering. Okay, many of you will take more advanced courses in software engineering later on, but coming out of this course, you should have a thorough understanding of the basic terminology, basic principles of software engineering, and a reasonably deep knowledge of some aspects of software engineering, particularly UML. Okay? Let us just go back for a second to okay, I'll go back this way. All right. So we were looking at the knowledge base. There's also a list of exercises in the book that are available. Now, one of the things you'll find is that some of the answers are available to students. Okay, there's an answer manual for professors teaching with the book, but that's password protected. There is an answer manual for students, so you can click on this and you can see the answers to the questions. You won't be assigned those questions, of course. You'll be assigned a different set of questions. But there's a selection of questions from the book which has answers on the web, so you can practice with those questions and see if you got the answer right. And if not, hopefully you'll be able to figure out from the answer what you did wrong. Okay? Any questions so far? No? Okay. Okay, I think that's pretty much it for a look at the book. Oh, one more thing. The source code for the exercises is available here too. So in the labs and assignments, you'll be able to download source code and use it. A lot of what this book is based around, and this course is based around, is working on modifying code that's already been written, or building on top of frameworks and other libraries that have already been written. So you have to understand existing code as well as design new systems, okay? And so the base source code for the book is here, and that's what we'll be using in this course. All right, any more questions? Great. Well, let's then actually start the main material. Should be right here. Okay, so we're going to start chapter 1. And the first thing we want to talk about is what is software. Now, one of the prerequisites for this course is that you have some experience developing programs, writing programs. Okay, so the University of Ottawa, for example, you will have taken CSI 1102 or CSI 1101, but most of you will have taken CSI 1102, which basically is the second course in programming, and you will have learned how to develop basic Java programs, etc. However, we want to talk about a few more abstract issues about what software really is, to try and contrast it and compare it to other things that other engineers produce. Because fundamentally, this course is about being a software engineer. It's not about being a programmer. Yes, programming is a key part of software engineering. We're going to go way beyond programming and get into much more deep issues of software engineering. So first of all, software is intangible. Okay? Software, unlike bridges, which are built by civil engineers, or televisions and other devices built by electrical engineers, or chemical plants built by chemical engineers, all those latter three things are solid things. You can see them. You see some plans, and then they have to bring in raw material and people with hammers or robots and bash them together out of pieces of metal and plastic and concrete. Okay, so you can really see those. Those are tangible. They break down. They fall apart by wear. Software is different. Software is pure information. Okay? Yes, you burn it onto CDs, perhaps, but you don't have to. I mean, software can be transmitted over the air, over radio waves. It is pure information. So it is intangible, and this makes engineering software quite different from engineering different kinds of hardware. And we'll understand some of the ramifications of this in a minute. One of the ramifications is that people find it hard to understand how much work it takes to develop a large software system. Many large software systems have millions of lines of code. Million line of code systems tend to be far more complex than typical, say, bridges or televisions or things like that. Okay? The amount of actual detailed design work that goes into a large software system tends to be much more than the amount of detailed design work that goes into the average, typical hardware system. Yes, there are hardware systems that are vastly complex, but there are also software systems that are even more vastly complex. The general public looks at a piece of software and sees a user interface for it and thinks it's probably relatively simple. The general public, and even people who are in professional roles, do not understand the difficulties of developing software. And that tends to put a lot of pressure on our industry. Now, why do things go wrong? Why do we have bugs? They just don't realize the difficulty of getting high-quality software out. Software is easy to reproduce. You can't, stamp off a few thousand copies of a bridge or a television really fast. Yes, you've got robots and assembly lines, and you can, bash out a few TVs in a few hours, but with software you can do it in a few seconds or less. Okay? So software is easy to reproduce. The cost of software is in its development, in the design, in the requirements process, the design process, etc., the testing process. The cost of hardware is, there's also design costs and requirements costs and testing costs, but the big portion of most hardware costs is in the raw materials and the labor for actually building, actually constructing the devices once they've been designed, in general, okay? And so that shifts costs to the design phase in software and makes the process of project management and managing the design process dominant in software engineering, much less so in other branches of engineering. And because of all the work goes into requirements design, programming, testing, etc., the software engineering activities, which are done by humans, the software industry is labor intensive. We don't have robots yet that can program computers. they've tried to make some automated devices, that we're a long way from really automating the software engineering process to any significant extent. Any questions? Okay, slide 2. Continuing talking about the nature of software. Untrained people can hack things together. Unfortunately, there's a history in the software industry of people developing systems. Perhaps they intended them to be small systems, but they get bigger and bigger as time goes by. There's a tendency for these people not to have training in the kinds of things that today we consider to be essential to high-quality software. Okay, in the early days, people didn't have any degrees in computing at all. There were only math and physics degrees, and that was fine. Developing small systems was fine. Later on, computer science degrees came out, and they were excellent degrees. They trained people really well, but the idea was that they trained people in a lot of the theoretical aspects of software development. Later on, they added software engineering courses because they began to realize that there was an engineering area that had to be talked about. But typically, people from computer science degrees have only had 1 or 2 courses in software engineering. Round about the early 80s, in countries such as the UK and Australia, and latterly in Canada in about 1997, we decided that we needed to establish software engineering degree programs and to boost the software engineering content of computer science and computer engineering degree programs, because we realized that we really need to teach much more about the engineering aspects of software development, so that we have people who are really trained to develop these high-quality systems, to reduce the bugs, to allow us to develop software within time and within budget, etc., etc. The quality problems are hard to notice. You can get people who have relatively low levels of training developing systems that seem to work until somebody tries to make a change. And when somebody tries to make a change, that's when the problems really start to come up. If you follow an engineering approach, you should be able to make changes to software relatively easily. Hopefully. People make changes to software without fully understanding it. That's the second key problem. Very often somebody's told, there's a bug, go fix it. Quickly root around the code, see something that looks as though it's the bug, fix it, but it has an effect somewhere else. Or they have to hack on something which doesn't really fit with the original design. And so now the design becomes more complex. And when that happens 1,000 times, the design becomes so complex that even well-trained software engineers have a hard time figuring it out, and they add new bugs as they fix other bugs. So software doesn't wear out in the way traditional engineering artifacts wear out, by being smashed or bits falling off them or chemically eroding. Software deteriorates by having its design changed over and over again, typically with errors. And these errors accumulate, and the design gets more and more complicated and difficult to deal with. Sometimes the changes are forced upon software by operating system changes. Microsoft comes out with a new version. Apple comes out with a new version. Whoops, got to change the software. Or maybe it's legal changes. The government comes out with new tax regulations. Whoops, got to change your financial software. Or a new regulation comes in the airline industry. Whoops, got to change my software for controlling aviation. Or some competition comes up. Whoops, got to make sure we change our software so that we can compete with the competitive software. So there's a constant demand to change software, and that's what causes design to deteriorate, because a lot of the changes are made without full comprehension of the original design. An engineering approach will help us to do this change process rationally and sensibly, and keep the quality of the design at a level where it can be changed over the long term. Questions? Okay, so about software then, much of it has poor design and getting worse. There's still a rising demand for software. A lot of things now are being done in software which in days gone by were done in hardware. A typical example. In 5 or 6 years, we're going to you purchase when you purchase a PDA, it'll have a generic radio receiver in it, which will be able to receive any part of the spectrum. and you'll be able to download software to make your PDA work as a television, or work as a cell phone, or work as any kind of radio-oriented device you want. It'll be completely under the control of the software. Okay, whereas right now there's special chips and hardware that does the work of tuning. That'll be done in software in years to come. It'll just take the radio spectrum, analyze it, and figure out what the signals mean, and same thing for the transmission side. That's, software-controlled radio just requires a little bit more of a boost in terms of computing power. Will be there, and that the world of software will take over what was once a hardware thing. People talk about being in a software crisis. What this means is that we seem to always be chasing our tails to try and get software to work, try and get the bugs out, and try and get our software developed within budget. A lot of software is developed way over budget. They might predict that a project will take $1 million and it takes $2 million, or it will be delivered next year and it takes 2 years. That's very common. It's a big problem for a lot of industries. We're getting better perhaps, but a few years ago, one of the major consulting companies did an analysis, and they came to the conclusion that $50 billion a year is being wasted in excess expenditures on software development that could be reduced if we followed a more engineering-oriented approach, particularly better testing, better design. Just a couple of weeks ago, that figure was updated, and it's now $60 billion a year. Okay? And so part of what we're trying to train you as software engineers to do is to be able to develop software in a better way to save some of that $60 billion. So hopefully in 10 years' time, there'll only be $30 billion of wasted money each year. So the key is we have to learn to engineer software. Any questions about the nature of software so far? Okay. A few general pieces of terminology. We divide software into a number of categories. One important way of categorizing software is whether it's generic, custom, or embedded software. Okay? So custom software is developed for a particular customer for a particular purpose. So a bank says, oh, I need a new system to deal with my evaluation of new loan applicants. That bank has specific rules and specific other systems it wants to plug that software into, so it contracts somebody or some company to develop the software for them, either internally, in-house, or externally. Generic software is software which is designed with the market as a whole as its target. Okay? So, for example, you go and purchase Corel Draw or Microsoft Word or something like that. That's generic software sold in the open market, also often called commercial off-the-shelf, okay, because it's commercial, it's available on shelves in computer stores, also often called shrink-wrap software, because it's sold in shrink-wrap boxes. And then a third major category of software is embedded software. This is software which is found in hardware devices, like cell phones, like digital watches, like personal digital assistants, palms, etc., like controllers. There's probably hundreds of embedded programs in this. I wouldn't put in the hundreds in this room. Probably 20 or 30 in this room right now. Okay, embedded programs. Some of you have. Although if we count every individual cell phone and PDA that some of you guys have, it probably could be hundreds. Okay, so there's vast numbers of embedded programs out there. Considerable numbers of generic programs. And somewhat fewer custom programs. However, it turns out that in terms of development effort, more work goes into the custom programs. Because every time somebody wants something developed custom, it requires a lot of labor to do that. Whereas the generic programs tend to, there's a lot of work goes into them, but it tends to be, you're selling hundreds or thousands or maybe even millions of copies of a generic program. So there's lots of copies out there, but the total worldwide development effort on that is somewhat less. And embedded software is even more extreme. There's lots of embedded systems, but there are sometimes thousands or millions of copies of each embedded system out there. So, for example, Nokia will develop its embedded cell phone software and put a copy of it in every single cell phone. And same thing with the cars. By the way, cars typically have dozens of separate little computers in them now, and each one has an embedded program, but General Motors probably only has, they probably reuse the same embedded program in many different models. So if you want jobs, you're more likely to find them in the custom arena, secondly in the generic, thirdly in the embedded arena. Any comments? Some software spans those categories. Okay, so for example, telecommunication system developed by a company like Nortel would have some embedded software and chips on its devices. It's going to have some custom software, and it will also sell generic software to the telephone companies that can be installed and run on its processors as well to some extent. Another major categorization of software is into real-time and data processing. Real-time software is software which must respond typically within milliseconds to events occurring. There's quite a lot of that around. Most embedded software is real-time software. So software that controls digital watches better be responsive to whenever the quartz system signals that it's going to change its second, to the next second. It can't sort of lag around and say, well, I'm going to hang around for a few seconds and reboot myself. Can't do that. It's got to be completely responsive second by second. Same thing with cell phones and things like that. Systems that control cars and other vehicles, obviously, must respond typically thousands or hundreds of thousands of times a second to changes in the environment, and then make decisions about how they control the devices. Safety is often a big concern in these real-time systems. The systems must be safe and they must be reliable. And so a lot of design effort goes into those aspects of these systems. Data processing software is software that has to do with running organizations and businesses. Okay, so your e-commerce systems, your systems for doing payroll, your systems for running banks, and things like that are data processing software. Big concerns there are accuracy of data. You do not want to lose thousands of dollars because of errors in your accounting system. And security. You do not want people hacking in and getting hold of credit card numbers or other personal information. Okay, now, security can be a concern in real-time software as well, but the dominant concerns in data processing for quality tend to be accuracy and security. Safety tends to be dominant in real time. Qualities like reliability are important in both, and usability are important in both, and we'll talk about those in a few minutes. Many pieces of software have both real-time and data processing aspects. Okay? Any questions? So we've talked a little bit about what software is. Now let's talk about software engineering as a discipline. What you see at the top there is my definition of software engineering. The book has a couple of references to other definitions, such as the definition by the IEEE. So my definition is this: the process of solving customers' problems by the systematic development and evolution of large, high-quality software systems within cost, time, and other constraints. A lot of words there. We're going to break it down and talk about the different aspects of that definition. Notice that the word programming isn't there. Okay? Programming is a part of software engineering, but software engineering is much more than programming. First and foremost, software engineering is about solving customers' problems. You've got to focus and figure out what the customer's problem really is and design or buy software that will solve that problem. Okay? There's a tendency in the old days for people to say, oh, let's start programming something right away. Well, that's not what we do in software engineering. We identify the problem, work out the customer's needs before we even think about doing any design. And sometimes the customer's problem can be solved better by saying, oh, well, buy this. Problem solved. There's already something out there that does the job. Okay, that's the engineering approach. No point developing it if it's already there. The engineer has to reduce the costs. We want to try and solve the customer's problem with the least cost. So our goal is solving the problems. Sometimes the solution is to buy. And adding unnecessary features, it does not help to solve the customer's problem, so we don't do it. We try and build exactly what the minimum is that will solve the customer's problem effectively. Okay, there's a tendency to, let's add this feature and that feature and make this really cool. Well, great, fine. You know, if you're trying to compete against another company, coolness could be a factor. But you only consider coolness a factor if it really is going to be important in the overall cost-benefit analysis. In order to solve customers' problems, you have got to communicate with people. There's a stereotype out there of the programmer or the computer person who sits in a cubicle all day and hacks away at software at a desk and you know, is a bit of a nerd or geek and doesn't talk to people at all and prefers machines. You know, that's the stereotype. We have to make sure that we don't fulfill that stereotype most of the time. I mean, once in a while, that's okay. I've done it. But in general, we have to be people persons because we have to interact an awful lot with our customers and users and other managers, etc. Okay, we'll talk more about that as the course goes on. There's a couple of sections in some of the chapters particularly focusing on people-oriented issues. Okay, so the definition of software engineering then is about solving customers' problems. And assuming we're not buying, the next stage is systematic development and evolution. So systematic is key. We're going to be doing things in a disciplined way, a way that has been shown to allow us to develop quality software by other people. We're going to base it on principles of software quality, software design, and mathematics and science, where they're available. Okay? And it's not just about development. Okay? We're not just going to develop new systems, we're also going to evolve or maintain systems. And in fact, most of the work will be in evolving and maintaining systems. We'll see that in a few minutes. Okay? Relatively rarely do you start from scratch. Okay, so in this systematic process, we're going to apply well-understood techniques in an organized and disciplined way. Well-understood techniques, that's what we'll teach you in this course. And we're going to apply well-accepted practices. There are a number of organizations that have published standards. Okay? Now, a standard is a document that is written down by an organization that everybody respects. And this standard says, here is how the general consensus of the engineering community is that you should develop a particular engineering artifact. There are standards in all branches of engineering. There are standard bridge designs in civil engineering, standard building codes for building construction, also civil engineering. There are standards in electrical engineering, and there are standards in other branches of engineering. And there are standards in software engineering too. There are two organizations that are leaders in standardization. There are others, but these are the two that stand out. First is the IEEE, the Institute for Electrical and Electronic Engineers. Okay, now, electrical and electronic, you say, well, we're software and computer engineers. What gives? Well, it's just historical. In fact, the IEEE is dominated by people in software and computer engineering, and computer science too, by the way. There is a student branch at this university and many other universities, and I highly recommend that you join it. And also the IEEE's Computer Society, which is the particular sub-organization that focuses on software and computer engineering. But they publish a lot of standards, and you can get a hold of those through the library if you're interested when you get into more advanced courses. Okay, if anybody wants to talk about the IEEE, by the way, you can talk to me. I've been a member since '87. I'm actually a senior member now. The ISO is the other standards organization. This has standards in many areas of human endeavor, and some of the IEEE standards are also ISO standards as well. Okay, any questions before we go on? Okay, continuing on with our breakdown of the definition of software engineering then. We said that we're solving customers' problems by systematic development and evolution of large, high-quality software systems. First word there is large. Now, you can build a bridge across a creek in your backyard. You can put a plank down. It's a bridge. Okay, that is not engineering. That is putting a plank down across a creek. Okay? It's the same thing if you go and write a program in 5 minutes to calculate something. That is not engineering either. You don't need to apply engineering principles to trivial things. You do need to apply engineering principles when you get beyond the level of triviality. So if the public was to be crossing this bridge across a creek. And therefore you have to pay a little bit of attention to whether this bridge is going to fall down and floods and things like that. That's when you have to start applying engineering principles. Or if the bridge is big enough, you have a lot of land and you've got to build a bridge across 4 or 5 meters. Well, you're going to have to start using steel and concrete. So you're going to have to start using engineering principles there as well. So most bridge building requires engineering principles. Most software requires engineering principles as well to be applied. Okay, so any software system that is developed for regular use in companies or to be sold on the market, there's more than 1,000 lines of code. You should probably consider seriously thinking in terms of software engineering techniques. That would be a ballpark, I would estimate. Okay, so the first thing is these are large systems, and large systems cannot be understood by one person. That's the key. There's going to be more than one person involved in the process. If you're building a little bridge, that's over a teeny creek, you can put the plank down yourself. But if you're building a bridge out of steel and concrete, you've got to have a whole team of people. Same thing with software. Maybe you can program 10,000 lines of code yourself, but somebody else will probably want to make changes later on. So immediately you have a team of people stretched out over time. Therefore, you need engineering principles to make sure you communicate the requirements in the design effectively with the other people who will work with it. So, again, we're back to the people thing. You're working with your users and customers, and now you're working with other software engineers. You're not just sitting in a cubicle coding away. A key challenge in software engineering is dividing up the work. If you're developing millions of lines of code in a system, you're going to have dozens of people involved at least, and the project management challenges dominate. You have to do a really good job of dividing up the work, making sure that all of the pieces will plug together properly when the system comes together. And finally, we always have to keep the word quality in mind as we're doing this. We talked about a few aspects of quality, safety a few minutes ago, and security. Well, more about quality in a few minutes. Questions? Okay, and the final piece of the definition then is we've got to do all that stuff. Focusing on the customer's problems, developing high-quality software, within cost, time, and other constraints. Okay? Engineering is all about reducing cost, reducing time, working within the boundaries of existing systems, existing environmental rules, existing safety rules, existing laws of whatever nature you want. Okay? Cost and time are the ones that everybody keeps in mind, but there are many other constraints as well. We have finite resources. We have computers that are only so powerful. There are fundamental limits on the kind of algorithms that we can actually compute. There are things that can't be computed in reasonable time. These are all constraints. The benefit of whatever we do must outweigh the costs. Okay, so you've always got to calculate how much are we going to save or make by producing something. On the one side, that's the benefit. And then the cost is how much is it going to cost us to develop the software and to maintain it over its lifespan. That's the cost. And purchase any hardware and other kind of stuff that's required. Okay? Balance those. The benefits of every little piece that you do must outweigh the costs of every little piece that you do. Otherwise, you just don't do the little piece. It costs too much. Okay? That's a universal rule of engineering, and it applies just as much to software engineering. We also have to worry about people competing to do the job cheaper and faster. That's also a cost issue. We have to keep our costs down to compete. And inaccurate estimates of cost and time are the bane of the software engineering industry. Okay? People find it very hard to estimate how much time it will take to develop software because the software is intangible, because the software is large and complex, because it's all involving human interaction and the requirements are not clear, and many other reasons why. But we nevertheless have to do the best job we can, and the engineering approach and the material we'll talk about in this book and this course will hopefully lead us to achieve better estimates of cost and time. Okay, so that's what software engineering is about in a nutshell. We're going to get into a lot of these issues in more depth as we move on. Software engineering is part of the profession of engineering. It has been in various different countries, as I said, since the late 80s, early 90s. In North America, Ontario started licensing people as software engineers in about 1998, and they started investigating the process a few years before that. Generally speaking, in order to have a recognized branch of engineering, you have to have accredited university programs. Okay, so we started our software engineering program in 1997 here at the University of Ottawa. We were one of the first in Canada. McMaster and Weston were also at the same time as us. Okay. Australia led the way. They've had software engineering degree programs for a little bit longer. The UK for a while under the British Computer Society. The US is a little bit behind Canada. They've had licensed engineers in Texas since about 98. But as a percentage of universities that offer software engineering programs, they're a little bit behind, but probably will catch up pretty soon. Okay, so in order to have be part of the profession of engineering, you've got to have software engineering programs. Why do we want to have software engineering programs? Well, because we decided that we want people to really respect the process of software development as an engineering discipline, because it does use engineering principles. Because we want to make sure that people who are designing software appreciate engineering principles, so we can improve quality and reduce costs. Because the fact that many of the traditional engineering activities, such as flying airplanes and building bridges, now require software, it's important that the software engineers be in the mix. Okay, there was a traditional approach to say, well, any engineer can develop the software for their artifacts. Well, that isn't really the case. You have to have deep training in software engineering, particularly to develop, say, the avionics systems for a new airplane. I mean, the bulk of the work in developing an airplane is the software developers now, in terms of labor and the design effort. Okay? So you have to be trained in software engineering to do that. Okay, so, and by the way, software engineering came out of computer science. Before there were software engineers, officially licensed and recognized as engineers, there were people doing software engineering. Most of those had computer science backgrounds. Most of the academic research was going on in computer science departments. At the University of Ottawa, we're one big happy family: computer science, software engineering, computer engineering. We've merged together in order to recognize this fact that we're really different aspects of a broader information technology profession. Engineering itself is a licensed profession, as I've mentioned. Once you graduate from an engineering degree, you don't have to get your license, but once you've got a certain amount of experience, it would be available to you following passing of perhaps an ethics exam in the US and other exams. And in Canada, you have to graduate from an accredited program and work for a few years, then you can get your license. Why get a license? Well, you only need a license if you're going to be developing, or you're going to be putting yourself out as an engineer, listing yourself in the Yellow Pages, for example, as an engineer, and doing contracting as an engineer. Okay, you can do computer programming without being a licensed engineer, but if you want to call yourself an engineer, you have to be licensed. And the idea is that the public, whether they be individual people or whether they be companies or governments, can say, okay, we want some work done, and we want to make sure it's done in following engineering principles, and we typically have safety issues or security issues or economic issues at stake. Let's make sure that we have an engineer do this work for us. And so they'll look up and see if you're a licensed engineer. If you're working in a company, you probably don't need to have a license, because the company itself will be the one that does the contracting. But it will be available to you, since our software engineering program and our computer engineering program is accredited. Assuming we keep our accreditation. It gets reviewed every few years, but hopefully we will. By the way, we're up for renewal this year. So they'll be coming later this month to assess our students and our faculty and our programs and our courses and our books and everything to find out if we still qualify. That's the entire faculty of engineering, by the way, including software and computer engineering. Okay. The original intent of licensing engineers was to protect the public against engineering disasters like bridges falling down. Now, the same thing holds. We want to make sure that, just like there's doctors that are licensed to help people's health and so on, we want to make sure that we can call ourselves a profession and guarantee that we have an appropriate level of education and skill. One of the key things in engineering practice is ethical concerns. Okay? Doctors have a Hippocratic oath. They must say, and this oath says that they promise to do no harm. Right? There's also a code of practice for engineering, and in particular branches of engineering, there are codes of practice. And the IEEE has and many other organizations actually, IEEE, ACM, and many other organizations have subscribed to a code of practice that is relevant for software engineering. And there's a reference to that in the book and on the web page. I recommend you take a look at that. You can't call yourself an engineer unless you promise to follow ethical principles such as, being responsible to your clients, being responsible to your management, being responsible to society and the environment, and many, many other things. Questions? In software engineering, we have to be concerned with people, as I said, 4 main categories, and we call these the stakeholders of a software project. The users are the end users, the people who will be using the software. Okay? The customers are people who buy the software. Not always the same people, but sometimes they are. There's been a tendency in software development to focus a lot on the customers, after all they're paying, and forget about the users. So a company is contracting to develop software, they're the customers. And they tell you what they want done, software developers, software engineers build it, give it to the users, and the users say, what the hell is this? I can't use this. Okay? So we've got to be concerned both for the users and the customers. And sometimes the customers and users don't talk to each other effectively. As software engineers, we have to talk to the users. Even if our customers don't really set it out in the contract, we still have to talk to our users and really understand their needs and prototype software with the users and test software with the users and so on. And we'll talk a bit more about that later on in the course. Other stakeholders, software developers, our peers who are working with us in the team, whether they be software engineers or user interface specialists or database specialists or hardware specialists or whatever involved in the software process, they're stakeholders, because if something goes wrong or they can't understand something, they run into trouble. Okay, so they're interested in the success of this as well. And of course the development managers, the people who are managing the process. They pay you typically, and they want to make sure that they have an appropriately developed software as well. So 4 categories of stakeholders. Occasionally they're the same person, i.e. you're developing software for yourself, but normally they're 4 different categories of people. And sometimes there may be many different groups of customers and many different groups of users. Maybe even many different groups of developers and managers. And so you may have to do an awful lot of networking and communication, and there may be political issues you have to deal with between different groups. It's all part of being a software engineer. Now, I talked about quality briefly. There are many qualities. Here are some of the qualities that we want to focus on in this course. The first one is usability, and I put it at the top because it tends to be the one that is neglected. How many times have you tried to install a piece of software and had difficulty installing it? It should be trivial, but it's often not. How many times have you tried to figure out how to use some software and had to spend a decent amount of time figuring it out, or even given up trying to use something? Hands up on that. Okay, a lot of you have had that problem. I'm surprised it's not everybody. Maybe you haven't used enough software. By the way, as a software engineer, get out there and use all the software of all the different types you possibly can. You need experience working with different pieces of software, just like a doctor needs experience working with different kinds of patients. Okay? And you'll find all the really bad stuff out there. Okay? And a lot of the badness is usability. Efficiency is another important quality. Efficiency is appropriate use of resources. You know, we don't want to use too much memory or too much disk space or too much network bandwidth. But, on the other hand, we don't want to spend all our time focusing on efficiency because we can get more powerful computers and networks often much more cheaply than the time it would cost us to boost the efficiency to work on the older equipment. So there's often a big trade-off there, and often people these days say efficiency is less important. But nevertheless, it still is a concern in many domains. Reliability is a big concern. In some systems, it's more of a concern than usability. For example, you're developing systems for controlling vehicles, cars, airplanes. They must not crash in more ways than one. The software must not crash, because if it does crash, the car or the airplane will crash. Okay? Therefore, reliability must be perfect in those kinds of systems. Very, very hard to achieve, but you've got to get there, because you just can't afford to sacrifice human life because of software problems. Maintainability is another concern. The software's got to be designed so that you can change it easily, because it will need to be changed. New operating systems will come out, new competing products will come out, new requirements will come out. And finally, reusability. A lot of work in the industry goes into redesigning the same old thing over and over and over again in different companies. Okay, or even within the same company. You know, I need a program or a class or a method to do a particular thing. I'm going to code it from scratch. You know, there was a day when, I need to sort something. I'm going to write up a sort algorithm. You don't do that anymore. You use libraries of code and classes and programs that have already been written. Okay? And the objective is to boost the number of available reusable classes and methods and libraries so that we don't have to develop, we develop less and less, and all we're focusing on is plugging things together to give the user the high-level functionality they need. Questions about these key qualities. These are qualities that dominate. They tend to be externally visible qualities, qualities that people will try and measure and look at. There are also some internal qualities we'll get to a little bit later on, which are sort of deep inside the system. Slide 14 now. It turns out that different stakeholders have different perspectives on what qualities are important. So, for example, the customer is mostly concerned with reducing cost. If they're the user as well, then they're concerned about usability, easy to learn, efficient to use, etc. But quite often, the customer focuses on cost above all other things. The user focuses on usability above all other things. The developers are concerned about maintainability. Can I design new things in this software? Can I change it? Can I reuse it? The reusability issue comes up there. The developer's immediate concern is not necessarily with cost or with usability. Although, as I said, as software engineers, we have to be concerned with these other areas as a professional responsibility. The development manager is more concerned about selling more, so the development manager is concerned about cost reduction, but also with adding all kinds of features to try and make the thing more attractive, which may not necessarily be useful for the user. And so sometimes there are conflicts about which qualities are more important. So the different qualities can conflict because different people have different needs, and because intrinsically we can trade off one quality for another. We can say, let's increase efficiency and really, really spend hours and days and weeks and months trying to eke out the last little bit of efficiency out of a piece of code. Often, what will happen if you do that is you sacrifice maintainability. You make the code more and more complex because you've added little hacks to add the efficiency here and there and everywhere. So now you can't maintain it anymore because you can't figure out, how it really works. Or if you try and make changes, it breaks the efficiency or something like that. Also, sometimes increasing efficiency can impact reusability because you make special purpose things that are maximally efficient in a particular context, but, well, they're not reusable in other contexts anymore. So reusability goes out the wall. Sometimes increasing usability can reduce efficiency. You might want to display more information to the end user over the network. Well, you're using more network bandwidth, which is an efficiency issue, in order to improve the usability. And so on and so on. There are trade-offs. One of the things the engineer has to do, therefore, is to set objectives. You set objectives. What level of usability do you need? What level of reliability? What level of maintainability? How much reusability do you need? You set the objectives for these, and then you design to meet the objectives. This is the same thing that other engineers do. If I'm designing a bridge across a river, my objective is, okay, how much traffic will this bridge need to carry? If it needs to carry a certain level of traffic, it'll have to be a 4-lane highway. If it's going to be trucks that are very heavy, it'll need to be a more solid bridge. Okay, so we set objectives in all areas of engineering. One of the things that we do by setting these objectives is to make sure that we don't over-engineer, that we don't produce a more powerful, more sophisticated system than we really need. Okay? Again, we have to work within cost, time, and other constraints. Sometimes one of these qualities is so important that we have to optimize. Okay? For example, in the vehicular system, reliability is so important that we want to optimize reliability. And sometimes we're going to say, okay, we're going to put maintainability on the back burner, we're going to put efficiency on the back burner, reliability is the key. You don't always have to optimize for a particular quality, but sometimes you do. Questions? Okay. Some of the quality issues are internal inside a system. You will have already been introduced in programming to the importance of commenting code and keeping code less complex. Avoiding nesting loops and if statements too deep. Those are deep internal aspects of quality that impact later on things like efficiency and maintainability. Also, we can think about quality in terms of short-term and long-term. Short-term quality issues such as does it meet the immediate needs or will it handle today's data? Unfortunately, sometimes focusing purely on short-term quality sacrifices the long-term. And so we end up with a system that requires a huge amount of work to keep it running later on and huge numbers of changes. Okay? For example, one of my first programming projects when I worked for the government of New Brunswick in the early 80s was to develop a system for managing the data that came from doctors. And the immediate needs were for a certain amount of money to be managed. But it turned out very quickly that that wasn't enough, and the system should have handled larger volumes of money. And so they had to do a lot of work to change the system, to fix it, to be able to deal with these larger volumes. Okay, so in the long term, we're going to be concerned with maintainability and customers' future needs. When we're doing software engineering, what we're basically embarking on is a series of projects. So we talk about software engineering in context of lots of projects. Some of those projects are new or greenfield projects. We'll talk about those in a second. But most of them are projects that involve changing existing systems. Several categories of those. Corrective projects, fixing defects. So you're told to sit down and fix a problem. Maybe it takes you an hour, maybe it takes you a week, maybe it takes you a month. But fixing projects is what fixing systems is one kind of project. Second major kind is adaptive. Okay, this occurs when you have to make your system work with new operating systems, new databases, new rules and regulations, new programming languages, whatever you might have. Enhancement, adding new features for users because the user says, well, I'd like to have this added. Sometimes they can be very big. Or re-engineering projects, sometimes called perfective projects. These are projects where you say, gee, this software is really bad. Okay, we need to go and clean it up before we do any further work. Those are the majority. The minority of projects are where you're given a fresh new problem where there doesn't exist any software and you're told, go out and develop whatever you feel like. Very rare, but occasionally it happens. And as I said, they're the minority of projects. also a number of categories of projects that are sort of intermediate. One of the categories is developing frameworks or libraries or bodies of reusable code that can be used by other people. Okay, we're going to focus on that a little bit in this course. We're going to give you a framework that I specifically wrote that can be used for communicating systems, client-server systems. Okay, and I wrote that specifically. It doesn't work as a whole. It requires additional things to be added to it to give it a complete, turn it into a complete application. Okay, so these are frameworks, and you have to plug together components to build fully functional systems. Each software project has a number of key activities. First of all, we've got requirements and specification. This is figuring out what the user really needs so you can solve their real problem. We're going to talk about that in chapter 4 of the book. Okay. Design. Design is a big part of all engineering. And we're going to talk about design using the UML language and many principles of design and design of software architectures and design of user interfaces. And all of that material goes from chapter 5, 6, 7, 8 of the book. Modeling is an activity which is focused on in several chapters, chapter 5 and chapter 8, and I think 7 or 8, and has to do with representing either requirements or designs. And again, UML is a key issue there. We're going to look at UML class diagrams, use cases, state diagrams in big ways. Programming is a big part of software engineering too. You're going to be doing programming in this course. In fact, the first lab is going to involve some programming. It's always that part of the software engineering process that is there. It can be a big part, but it's only a part. Quality assurance is a key part. We're going to look at that towards the very end of the course. And deployment is how you distribute software. We're not going to look at that too much in this course. Managing the process, we're going to talk about some issues to do with that. The last chapter of the book is about managing the process. I'm actually not going to really get into that in this course, but it's available for you to read, and it will be covered in other courses if you're in the software engineering program. Okay, I'm going to wrap up this lecture by just giving you an overview of the 8 themes which run throughout the book and the course. The first theme is understanding the customer and the user, the people-oriented issues in software engineering. Okay? The second theme is basing what we do on principles and reusable technology. Okay, so we're going to be taking class libraries and taking well-understood principles and learning how to apply them properly to develop software using an engineering approach. We're going to be focusing very heavily on the object-oriented way of doing things, which is basically the modern way of doing things. There are other approaches, but object orientation is the key. Implementation will be done in Java, for example. And UML is a language which you'll be learning in some depth, but it's not a programming language, it's a visual design language. Evaluation of alternatives, which is a key issue in engineering. There's one way of doing it, there's a second way of doing it, there's a third way. Which is best to reduce the cost to better solve the customer's problem? Iterative development. Let's not try and do everything at once. Let's do a first little bit, see if it works, give it to the customer, then we'll move on to the second part of the customer's problem and the third part. Communicating effectively using documentation. We have to write things down, but we don't want to write down too much. We want to write down just the right things. And finally, risk management. Making sure we're always aware of the problems that could arise and how we can combat those problems and head them off at the pass. Okay, so that's